is getting compressed by the bottom. And then we have NAB here. And remember, I said that you could either draw NB here like this, or Brandon prefers to use ones that are drawn away. Right? Either one is fine, but only draw one of them. Oh, this is leaking. Okay, let's take a look at NAB then. So they decided to have NAB go from A to B going down. If this is going down to the right, should this one be equal and opposite going up to the left? Mm-hmm. Yes. Okay. What are some other things we need to have on this free body diagram that aren't here? What's the number one? The theta. We need to have the angles, right? Because right now, I don't have any directions of these guys, right? I need to make sure I have my forces labeled with directions. So let's take a look. This right here, the angle between the horizontal plane and this is 30 degrees. So the surface right here, and my normal A is drawn perpendicular to the surface, right? What's perpendicular to the horizontal plane? A vertical plane. So that means this right here is 30 degrees.
So, one question. So
yeah.
We wouldn't draw the normal AB as instead having it be the force on B of B on A. Like
actually, I was going to talk about these in a little bit, but right now I'm just on this one. Okay. So can we just talk about this one first? I want to make sure that people are comfortable with the angles. So the angle here of 30 goes from the surface to the horizontal. Mm-hmm. So the 30 is going to lie perpendicular to the surface and perpendicular to the horizontal. And that's the same thing here. Normal B is coming in. The degrees right here is 15 degrees. 15 degrees between the inclined plane and the horizontal. So that means the 15 degrees is going to lie between the normal, which is perpendicular to the surface, and the vertical plane, which is perpendicular to the horizontal. Chris.
I'm sorry, how does that work out with the triangles, like the complementary
It's when
angles?
When the angle between two things, right, if you know the angle between two lines, mm-hmm. the angle between two lines that are perpendicular to those two lines is the same.
Okay.
So you have two lines, you find two lines that are perpendicular to them, and it's the same angle. Okay. Play around with it, I would say.
Yeah.
Okay, so now let's move to NAB and NBA. So notice that Armando called it NAB and Brandon called it NBA. If I want to call these different variables, I'm going to have to make sure that I make a note that they're equal to each other. Otherwise, I'm introducing a new variable. And I think here, I already wrote NAB is equal to NBA. Mm-hmm. So as long as I wrote that, that really only represents one variable. I probably would only use one variable because I don't want to confuse myself. So I would call this NAB. So when I look at my picture, I only see one variable. Okay, now the angle. And Haley, I think this is where your question was. We don't really know if cylinder A is pushing down on B or B is pushing down on A. We don't know. And we don't know if it's going to be horizontal or not. So Armando made a call. He said he thinks, well, no, this isn't correct. This is probably what you were asking for, Haley. Because if the load is coming from B to A, it's got to be drawn to A. Armando, do you see that? This load right here is a normal coming from B to A.
Isn't asking for A to B?
Well, if you're asking, what do you mean, A to B? You mean this thing?
Yeah. Because it asks for the force exerted by A on B.
Right, and then it wants the reverse too.
Oh.
Which cylinder did you draw though? Did you draw A or did you draw B?
This one's A. So B is pushing on A. It's a compressive force. A is pushing on B. It's got to be a compressive force.
Yeah.
Did anybody have any questions about the direction of NA? Here's the surface, right? Oh, let's get a different color. The surface is right here. Everybody look up here. The surface is right here. The surface is pushing on the cylinder. So you agree with this direction, don't you? Does everybody agree with the direction going up to the right? Because the surface is pushing on the cylinder. Well, wouldn't you say the same if the cylinder is here? If this cylinder B is pushing on A, shouldn't the angle be going up like that?
Yeah.
Right? Maybe you don't think it's going up. Maybe you think this big cylinder is here. Well, then the force has got to go down to the left. But either way, it's compressing cylinder A. It's not pulling it away. It's compressing it. A is getting compressed. A is getting compressed from here and here. If this was a balloon, wouldn't it get compressed? It would be smushed. But it's a cylinder, so it's not smushed because it's stiff. But this cylinder is being pushed by this and pushed by this. And if it was a marshmallow, it would be squished completely because it's a compressive force. So what is this experiencing? Is it experiencing tension or compression? Compression. Compression where? From the bottom and from the left side. Everybody gets it? So when you analyze the cylinder, you have to have two normal forces. One coming from the inclined plane and one coming from the other cylinder. When you analyze this cylinder, you have a compressive force coming from the inclined surface and from A. The only thing we don't know is we don't know if the angle is like this or like this. We just have to call a shot. So what we did is we said, we assume it goes this way. And if it goes that way, and if I draw NAB or NBA, whatever the hell, I mean, if you want, just call it N. Because here's NA and NB. Call it N, and then you don't have to think about AB or at all. And then go back to this and just call it N. If you don't like the whole thing about A to B, B to A. You just need a different variable. So we said that N goes from here to there, which means it's got to be equal and opposite. It's got to go down to the right now. David?
Wouldn't it be a little bit important to differentiate A and B and B and A because they're going to have different direction? Like one's going to have opposite signs of the other.
Say that again? Wouldn't it be important to distinguish between NA and NB? Is that what you said?
NAB and NBA because they're going to have opposite directions, and we're only looking for B to change, or vice versa.
Right. So in this case, this N here, how would you describe that? Is that? I'm going to erase this circle now. What is this force that I drew represent? It's the force of B on A, correct. And what does this one represent? The force of A on B. Does everybody agree? This represents the force that B is putting onto A. This is the force A is putting onto B. But in the end, their value is the same, right? They're going to have the same magnitude, 20 pounds, or whatever it happens to be, right? So when you solve for it, whether you solve for N here or here, they're both going to have the same value.
The magnitude is the same.
The magnitude is the same. That's correct. And the direction is going to be different.
Yeah.
So in the problem, which one are they asking you for?
A onto B.
So they're asking for this one, right? But as long as you have them drawn, in the end, what your answer is in these statics problems is your free body diagram along with the values. So somebody's going to look at the free body diagram, know the directions, and they're going to see the magnitude that you calculated. Kelly?
No, that, I was just
Same
going
thing?
to say the same thing, but it seems like you would want to know whether it's a positive or a negative value of that. But you're saying just look at the picture and not represent it with a sign?
You're not going to have to represent it with a sign. We're jumping ahead a little because if you get a negative in statics, it doesn't mean a negative. We're not going to go there yet. Let's wait. Let's answer that question when we get to number crunching at the end. Does that sound okay? let's wait, because a negative number means something, okay, but we don't know yet. So there's still some more missing here. What else is missing? Okay, I don't have the axes at all, and I don't have any direction of that n, right? So I need to have some kind of direction. What do we want to do?
Theta.
How about we just put a theta? And then where's theta here? It's between n and what? The horizontal axis. And then I need to put my axes in. Let me go back to David's question again. If they want to know what the value is for the normal from A to B or B to A, it's the same value, right? Regardless, they're equal and opposite. So the magnitude is going to be the same. The only thing different would be its direction. Right? Okay, so now let's draw a free body diagram going from A to B. Sorry, let's draw a free body diagram of A and B together. So I don't know where we are, but let's start. Chris, we'll come back. Chris, so what forces should I have in the combined AB free body diagram? The weights. So I'm going to put both weights in. Elliot, what else should I have? Which one? Okay, A and B. So I'm going to have the normal A, and we know the angle is 30 degrees. And I'm going to have the normal B. And what's the angle here, Elliot? 15 degrees. Okay, Eric, what about NAB? Should I draw it?
Yeah, put the normal A onto B.
Okay, but if I draw the normal from A onto B, then I would have to draw the normal from B to A, and what would happen to the two guys?
Cancel out.
They would cancel out. Because what did I say that force becomes in the end?
0.
Not a 0, but it's an internal force. When these two are separated, the forces are considered external to the system. But when the two things are touching here, that force is inside. There is a compressive force in here, but they're equal and opposite, so they're canceling. So it becomes an internal force, not an external force. So you do not put it in the free body diagram. Kyle.
So the only numbers that you want to put in there are just like your angle numbers. If you know the weight value, you just use the
Right, so we know the weight, right? So what were the weights?
Well, I mean,
392, so we could put
it's kind of like a preference thing, I guess.
392 newtons, was it? And what was the other one?
82.9.
882.9 newtons. So here this would be 392.4 newtons, and this is 882.9 newtons. Ask your question again, Kyle.
Well, I guess I answered it. We should put, if we know it, we should put it on there. Or can we just leave it?
You can leave. You don't have to write it because you wrote it on the sheet already in the setup. You already wrote it, and you could use the variable. If you want to put it in, you could.
So can't we just combine, can't we just have it be two forces, the weight of the combo and the normal of the combo?
What, say that again? Combo? What do you mean?
Just add the weights together and have it be one force for the weight.
It's
and
not
have
a single rigid body, so you can't do that.
So, Haley, are you saying that could we just do this? Is this equal? Weight A, weight B,
Yes.
normal A, and normal B? That's what you're saying, right?
And just get one normal too?
You mean put these guys, you could sum up the Y's, and then you'd have two X's? But let's just take a look at the two differences here. Remember, what are the two different kinds of motion you could have? Translational motion and rotational motion. If I have this free body diagram where all these forces are pointing to this point and all these are coming off that point, what kind of motion could this experience?
Translational.
Only translational, right? This thing's either going up or down or to the side. It's not spinning. But let's take a look at what's happening here. There's a force coming here. There's a force coming here. These guys have a distance between. Can't these cylinders actually have a rotational motion too? Okay? So because they can have a rotational motion, we can't reduce this to this. And the physics term would be, is that my phone or something? No. Oh, it's some construction thing. Because nobody was shutting it off, so I thought, oh, is it mine? Peter, your answer is a physics answer. It's great. This is not a rigid body. These two things are independent to each other. They can move relative to each other. So you can't reduce it to one dot. It's not a rigid body. But another way to think of it in terms of moving is these forces could cause these things to spin relative to each other or move relative to each other. This implies that it's only one spot. So this is not correct. That's what your question was, Haley, right?
Yes.
So we had 4 unknowns. So let's go back to find. What did they want us to find? We never filled in that find area.